can't think as people do. The machine is different.
Being! What marvelous being! How gratifying! How gratifying!
All right. Can you hear me all right? Good evening and welcome to tonight's special event. Thanks, Ty, for the introduction, and thanks to COSI for hosting this. So, as Ty mentioned, I'm John Beacom. I work at Ohio State University. I'm here with three of my colleagues. And first, I'm going to give you a little bit of an introduction to what particle physics is, to take you from the experience of everyday life to what happens when you're operating the Large Hadron Collider and finding the Higgs. So something happened in between, and I'm going to try to fill that in a little bit. And then afterwards, the four of us will try to answer any questions you have about the film, about physics, about cosmology, anything you want to ask. We'll try to keep those questions short and keep our answers peppy. And then afterwards, we'll mingle around in the lobby and you could ask longer questions. So the four of us, I mentioned my own name. Professor Stuart Robbie is also here. He's an expert on particle theory. Professor Linda Carpenter is also here. She's another expert on particle theory. She's also a close personal friend of the person who made the movie, so she can tell you all of the stories. And we're also joined by Dr. Mauricio Bustamante, who's a postdoctoral fellow in CCAP. So, you hear me. I think, I talk, you hear me, you understand me. That sounds so everyday, it's totally unremarkable. But the fact that that works at all tells you that there must be simple laws that underlie how everything works in the universe. Why? Well, because my brain is basically just a few pounds of pink goo, and out of that goo came an idea to say something, and then all kinds of complex things, and something came out of my mouth, traveled through the air as a pressure wave, landed on your ear, which is sensitive to incredibly small changes in pressure, was processed by electrical receptors in your ear, in your cochlea, turned into your brain, and that blob of pink goo between your ears received the thought and understood it. So it's incredibly complicated, but it works. And it gives a hint that there must be simple laws of the universe that govern everything, otherwise we'd never be able to make any sense. If there was a law of the universe that only applied to me, and a law of the universe that only applied to you, it seems incredibly unlikely that we could communicate. It only works because we're actually governed by the same laws, not just of physics, but also of biology. So once you have that idea, you can start to look for simpler and simpler things. And so, for example, if I take a coin, and I drop it, and I take time how long it takes, and then I do it again, and again, and again, then it's almost the same every time. It's more simple than us when it shows repeatability, and that gives a clue that something even simpler is going on, and it gives us an idea that we need to go to much smaller things and look at the simplest interactions. And if we understand the smallest, simplest things, and the simplest forces between them, we might be able to eventually understand all of the complexity we see. And the way we understand those smallest things is with a particle collider. And the way it starts is, you take a penny and a hammer, and you just beat the snot out of it, and try to break it into smaller and smaller pieces. And you get some smaller pieces eventually. By the way, don't tell the federal government that I said that, because it's a crime to destroy, a symbol of the U.S. like that. But eventually you can break this into smaller pieces, and then you think, if I had a bigger hammer and I applied more energy, I could break it into smaller and smaller pieces. And the question is, does that process ever end? For thousands of years, people thought that process did not end. We now know it does. We now know that this penny is essentially made of Legos. And those Legos are indestructible little bits that we think we can't take apart. So what are those bits and how do we get there? So let's recapitulate basically the science classes you had in high school. First, wood shop or metal shop, taking things apart, beating the heck out of them with a hammer. That's good. Then eventually chemistry. People figured out that these are made of molecules and atoms. And then eventually physics. And people realized that those atoms are made of electrons, which, by the way, electrons we think are still indivisible. We've been unable to take them apart despite our greatest attempts. The nucleus, that was not too hard to take apart by using a particle collider. So obviously a nucleus is too small for a hammer, but if you smash two things together, you can take them apart. And the nuclei turned out to be made of neutrons and protons. And then we took those apart with a higher energy collider. And those turned out to be made of quarks. And despite our best efforts, we have not been able to take those quarks apart. So you just learned a law of physics, and that is that if you want to take something apart on a smaller and smaller scale, you have to put in more and more energy. And if you think about what I did with the hammer, that's not surprising. Basically, it's actually more than just a vague idea. The size scale that you can resolve with a particle collider is basically proportional to 1 over the energy you put in. So the particle colliders that people had decades ago had a relatively low energy. The ones that they have now with the Large Hadron Collider have tremendously higher energy. And that enables them to see finer and finer scales. It's sort of like what happens when you go from an optical microscope to an electron microscope and so on, like that. So that's one law of physics you just learned. Another one you already knew, the most famous equation in physics, which is Faraday's law? No? E equals mc squared. That's the other law you know. So a funny thing happened when people built these colliders. Not only did they take apart all of the known constituents of matter, so by the way, that brain, that coin, all of those things ultimately just made of quarks and electrons. Everything ultimately just made of quarks and electrons. Not only did they find those things, they found a bunch of things that they weren't looking for. They found things that are not included in ordinary matter. So for example, through colliders and other means, we discovered neutrinos. Not a part of ordinary matter, but it's a particle that exists. And then we discovered heavy, unstable cousins of the electrons and the quarks and the protons and neutrons. Those particles exist for a fraction of a second, and they're like the other particles, but they're not part of ordinary matter. And that's another thing you can do with colliders. How much energy you need to make them is given by E equals mc squared. So again, you want a higher energy collider. The last thing we learned from colliders is what to do with all of this information. And that's where people like Professor Rabi and Professor Carpenter especially come in, is systematizing all of this knowledge. So one of their questions is, okay, you figured out all of these particles and you figured out something about their masses. Where did those masses come from? And the answer to that question for some particles appears to be the Higgs boson. And that's why it was so important to find the Higgs boson, to understand how it is that particles like, say, an electron get their mass. And finding the boson helps understand that. And it also gives us ideas about what physics we might not have found yet. And that's something we can talk about at the end of the movie. So I encourage you to think about questions during the movie. We'll try to have the questions and answers be sort of rapid fire. If you have a long question about, okay, I have this theory, it's about time travel, and first I wanted to sidebar about this one time I saw this alien. Okay, save that for the discussion outside. Good example of a short question is, okay, it's a little spoiler. In the movie, they found the Higgs boson. Did I ruin it for you? Okay. In the movie, they found the Higgs boson. Dude, is it still found? Or did it go away? Was it all a mistake? That's a good question. Or what else are you looking? Now you found the Higgs boson. What else are you looking for? Why didn't you turn off the collider? Those are good questions, and we can give short answers. So without further ado, welcome to this event. Oh, one thing I forgot to mention. Our colleague, Paul Sutter, hoped to be here tonight. Unfortunately, he's ill. So Paul has a special appointment. He's half-time at OSU, and he works with us in the Center for Cosmology and AstroParticle Physics, and also the Department of Astronomy. And he's half-time here at COSI as their first ever and new chief scientist. And this is bringing greater connections between the outreach and education efforts at places like COSI with the cutting-edge research that we're doing at Ohio State. And Paul will be a central part of that, so look for lots of other joint events. So without further ado,